Okay, Danny, we'll go ahead and start. Good afternoon, everyone. Thank you for joining us today for Sound Control in Construction presented by Homasote Corporation. This is worth 1 credit under the HSW category. My name is Andy Bredesen. I'm with a sales agency called Preferred Marketing Associates, and we've been representing Homasote for 6 years. I'm based out of Baltimore, and we'll be doing this presentation with 2 of us today. I'm joined by Steve Gleason from the tech desk. He is the answer man on all things technical, and happy to have him joining us. And it makes the presentation, I think, a little bit easier because you're listening to 2 people and not just 1. For those of you joining us today, and Danny provides the list, we're going to be sending out a Panera gift card for lunch to wherever you guys choose, and then for your distribution. And thanks for joining us today. So Steve will do certificates if you want a certificate, and as soon as we get the AIA numbers, Steve will also be issuing the credits same day. So if we get that from Danny today or tomorrow, it'll be an immediate response. So this is a 1-hour course. Design professionals will gain practical knowledge of sound control and the many health and safety benefits it has for architects, builders, and occupants. We're going to discuss the building code criteria, guidelines, including strategies to meet the requirements through various methods. And by the end of the course, you'll be able to evaluate different sound control strategies and specify the ones that best fit each project's needs. The learning objectives are to discuss how sound control can help reduce noise pollution, sleep disturbances, litigation costs, and privacy issues for building occupants and owners, and review both the IBC and the IRC codes to address sound control issues that affect the building occupants. We'll describe sound control strategies to alleviate the noise-induced sound damage by utilizing things like mass and decoupling, absorption, acoustical sealant, and other methods. And then finally examine sound control design methods for walls and floors using sustainable and mold-resistant cellulose fiberboards made from recycled materials. The agenda is these 5 categories: sound control in the building industry, building code criteria and guidelines used to assess sound control theory and the terms that go with it, the strategies of sound control, and finally addressing sound control issues. So starting off, let's look at sound control in the building industry. There you go, noise pollution. It's everywhere, and it was everywhere before it became code in 2003 to address it in construction. But so many times, especially in the last 10 years or so, people are moving to more metropolitan areas. Those without cars want to be by the metro line. And so the builders are building high occupancy 2-over-2 townhomes and condos in communities where there's retail and there's restaurants and there's also noise. And so it affects all of us. So the importance of sound control is different to who you are in the relationship to it. But to the consumer, it affects your sleep, it affects your productivity, and it affects privacy. Whether you're in your own condominium or apartment or hotel. To the architect, we want to make sure that we have code compliance. And for the builder, we want to make sure that we build to code so that we avoid potential litigation and potential remediation to make them up to code. And that all affects the builder's reputation. So cost considerations, when you talk about litigation, sound is one of the top 3 litigation costs behind mold and foundation settling. One major builder reported that they have up to 14% sound failures. And it always does not have to do with the product that they use to control sound, but its installation, and is it done correctly? And when you talk about remediation costs, if a building does not meet code, it can exceed $32,000 per multifamily unit to bring it up to code. So talk about reputation. I'm sure if we were in a room and I asked you to raise your hand for anybody that goes on to crowdsourcing formats like Yelp or others, you can relate to this. You don't just go looking for great restaurant reviews, but sometimes people go and complain. and this one we pulled off the internet. The room was clean, the staff was friendly, but the walls must have little to no sound barrier. We would clearly hear conversations among other activity next door, and the guest above us sounded like he was walking in our room. We had to be moved at 12:30 a.m. We're never going to stay at this facility again. If you're the owner of that hotel, you can't afford to have this put out there, and yet it's done every day. And I would say, just from personal experience, I stay in hotels quite a bit, and even hotels that are newer and built after 2003, I still really wonder if they were built to code with regard to sound, because so much of the time you can hear conversations so easily in the room next door. So where do we need sound control? I think we need it everywhere, but specifically, let's look at this. So multifamily is what we're addressing here. Apartments, condos, dorms, senior housing, duplexes, townhomes, but not just residences. It's also for the offices, hotels, and education facilities and healthcare. So now let's look at the building code criteria and the guidelines that we use to assess that sound control. So IBC 1206, and this was changed a few years ago. It was IBC 1207. Up until recently, they changed it to IBC 1206, but we addressed two different ways of looking at sound. First is airborne sound. So walls and partitions and floor and ceiling assemblies separating dwelling units, and also now separating sleeping units from each other or from public or service areas shall have a STC, sound transmission class, of not less than 50. And it was in 2015 that they added sleeping units to this description. The second is structural borne sound. Floor and ceiling assemblies separating dwelling units and sleeping units from each other or from public or service areas shall have an impact insulation class, an IIC, of not less than 50. So that's the IBC. And now we look at the IRC, the International Residential Code. They address both of these same sound, air, and structural borne, but they only require a 45. And let me back up a second and say that if you do field testing for the IBC, all you need is a 45 as well. So you can do it by, you can get it to a 45 by doing the field testing. There are two slides here regarding LEED. The first one is regarding minimum acoustic performance for exterior noise. So it says that for high noise areas, implement acoustic treatment and other measures to minimize noise intrusion from exterior sources and control sound transmission between classrooms and other core learning spaces.
Is now joining.
The second lead slide is regarding minimum acoustic performance, classrooms and core learning spaces. So here, for each room, confirm that the total surface area of wall panels, ceiling finishes, and other absorbent finishes equals or exceeds the total ceiling area of the room. And this is going to be noted with it being greater than a noise reduction coefficient of 0.7. And we'll describe NRC and noise reduction coefficient in a few slides. So now, what are the sound control theory in terms? I like this. When is something too loud? Well, I think this is very subjective. Something may be too loud for me, but not you, or vice versa. So it's subjective to the person. It's said that noise-induced hearing damage is related to the duration and the volume of exposure to that noise. According to the National Institute of Occupational Safety and Health, the safe exposure limit is 85 decibels for 8 hours per day. And a decibel is a unit that measures the intensity of the sound. Here's some common decibel levels. And on the right, we're showing a sound pressure level meter. The one on the far right is something that is probably a little bit older today, because right next to it, that's an app right there. That's one of so many apps you can just download from the App Store. Most of them are no charge. You hit the button and you can just see what decibels you've got right where you are. And so sometimes on a job site, you could be in the production zone, and when the windows are put in, either before they're put in or after they're put in, test that level, see what that noise is that's coming from outside. But the average home is 60 decibels, the average office 60. If you really want to get the most accurate measurement, it's best to hire an acoustic consultant who's got more sophisticated equipment to tell you where you are. but it's nice to have the app on your phone. And now talk about sound transmission class specifically. STC ratings assess the material or an assembly's ability to resist airborne sound transfer. The higher the number, the better the resistance. So let's look at some of them. The STC ratings on the left. So if you start at the first one at 25, you can hear normal speech and it's understandable through the wall or the floor. Obviously that is poor. And as you move up the scale there, you get to a 40. Loud speech is audible, but you can't really make out what's being said. I'm not so sure that I would call that good. But if you get to 50, that's our goal there for code. Loud speech is barely audible. That's considered very good. At least it's a benchmark for code to get us to a level where it's acceptable. And you get above 55, loud speech is not audible. We're seeing also that in some of the major cities like New York City's and other, for buildings that have condominiums that are selling for $1 million, they're willing to put more money into the wall and floor because they want to get that floor up to an IIC of 60 or greater. And it's too important for them not to have their owners of these properties satisfied. STC testing, Steve's going to take this one.
Sure, thanks, Andy. So before we get into the nuts and bolts of how you would graph out an STC test, as you can see on the right, just a few words about testing in general. You're designing sound control components to a wall or a floor ceiling assembly. You're going to find that there's a lot of acoustical spin out there in the marketplace. Get your hands on a sound test and read it and find your best way to understand it. There's going to be a lot of verbiage in there that's going to give you hints about or real data about how this assembly is designed relative to what your needs are. Things like fastener size and spacing, joist spacing, joist size, types of insulation, types of drywall. IIC and STC testing documents are important. Let's take a look at an STC test for a wall, though. The way they do this is they build the wall in a sealed assembly between two acoustically balanced rooms. They're going to blast out 115 decibels in the source room and measure it in the receiving room and graph it out as you see it here. You'll see that the bottom horizontal axis is frequencies and the vertical axis is sound transmission loss numbers. And remember that the higher number is the better number. They'll graph that out as a broad frequency spectrum of sound, and that's the blue line that you see. Then the reference curve, the red line, which is the performance of, say, a 9-inch brick wall. We'll introduce you to that brick wall shortly. They'll raise that in the software until there are no more than 32 total deficiencies below it, or 8 deficiencies at one frequency, which is usually a frequency of 125 hertz. And where that line intersects with 500 hertz, that's your single STC number. But always remember that the transmission loss numbers give you a better story about what's going on. So look below it and above it relative to the spaces you're designing. Andy?
Thank you. So now impact insulation class, IIC. IIC ratings assess the ability of a material or an assembly to resist structure-borne sound transfer. We're talking about floors here. The higher the number, the better the resistance. And in multifamily, it's much more of conversation about floors and the person living above you making that noise than it is for the walls. They're both important, but floors tend to be the bigger culprit. Steve?
Sure. So an IIC test is graphed pretty much the same as an STC test, but the sound is a different situation because remember with the airborne sound, STC, that sound wave has been generated and it comes across the room as a sound wave and strikes the wall. With an impact sound, it's happening right at the surface of the floor. So there's a picture of the tapping machine that they use. And again, they measure it at 500 hertz. The problem with IIC testing is that it does not accurately model what's going on in the low frequencies because obviously it's tapping hard. Somebody who's walking across a floor is actually flexing that whole floor. The sound is developing in the cavity of the floor ceiling assembly and it's a low frequency sound. So that's somewhat problematic and it's just something that you have to look at for when you look at those transmission loss numbers, you can really see what's going on. Andy?
So noise reduction coefficient, we mentioned this earlier when we talked about the lead slide, and noise reduction coefficient, NRC. This rates the effectiveness of a material absorbing sound So now we're not talking about sound going between spaces or between rooms or apartments. We're talking about internal to that room. A zero NRC means it's mostly reflective. A 1 means it's mostly absorptive. So it's going to go from 0 to 1. Two examples are that drywall has an NRC rating of 0.05. It's easy to understand that. It's very hard and dense, and it's highly reflective. But fiberglass, on the other hand, is a 0.9 because it's almost perfectly absorptive. So there's types of acoustical improvement. You have sound control barrier between spaces that we mentioned, STC and IIC. And then there's acoustical improvement within that space, like the photograph there. We want to stop noise from reverberating around that room, disrupting all the other people that are trying to have conversations. And so we're talking about absorption through noise reduction coefficient, and diffusion is another method or process we can use to help make it more acceptable, and we're scattering that coefficient. So here's some sound wave diffusion examples that you have in the photographs there. Improve the acoustics by breaking up the reverberative pattern of the sound wave. Irregular features, as shown there, redirect the sound wave and they scatter it. Flanking sound. This is a problem. So sound passes through small openings. A 1/16 of an inch opening in the bottom of an STC rated 50 wall reduces that STC rating to 32. It's such a small thing to overlook or not accomplish, and yet it short circuits the entire project, taking it from 50 to a 32. So what do? You wrap backs of outlets and switches and recessed lighting units with putty pads. You float the wall edges and seal those gaps with acoustical sealants. Think about the ductwork in walls and in ceilings and creatively route that. And then fit doors well with side seals and tight sweeps if you really want to control the noise. And so often in commercial office spaces, it's not something that you're doing on these doors. There's gaps beneath them. So if sound is a critical thing to block off in a particular boardroom or conference room, those things would have to be dealt with. And use pattern matters. So how spaces relate to each other will dictate the sound attenuation measures. You might have in a multi-use building, rock and roll music in one room, and on the other side might be very quiet music for some counseling. So what the room is used for matters, and then we're going to address that controlling sound by what we put between the floor and between the walls for different uses. Now let's look at sound or strategies of sound control. What are the strategies? So here's the hot list, the good topics. Mass, we're going to use mass, and we're going to damp that mass to stop sound. We're going to use decoupling or a mass air mass assembly or enhanced gypsum wallboards or absorption with the insulation, other membranes, and finally acoustical sealant. Steve?
Sure. So one of the things we're trying to do with this presentation is to give you a better idea of some of the dynamics of sound control, to kind of take the curtain aside as to what's happening. As we go further through, starting right here, we're going to be showing you some of the ways that this really works. If you can understand how the dynamics work, it'll be helpful to you in making these designs. We start with mass law. Mass law tells us that when you double the mass of an assembly, you gain 6 decibels of transmission loss. That's a limitation. A 9-inch brick wall is going to stop a lot of sound because it's non-resonant mass. But we can't build with 9-inch brick walls. So what we're going to be doing is trying to figure out how to get around mass law using conventional construction materials, and not having to just rely on straight mass. As we go forward, that's exactly what we're going to do. Andy?
So starting with mass as the first method, we can increase the mass of a secondary subfloor and increase the STC rating. And you'll see here that there's lightweight gypsum being poured. In this example, perhaps it's acceptable some places, but not most, meaning that typically an acoustomat gets put down and then a thickness of the gyp pour over it to equal what they need to gain the STC and IIC. Also, here you're adding just tons of moisture to the building, and then you got to worry about drying it up. But it's one way, and this is one of the ways you can increase that secondary subfloor. Steve?
So what's the first thing that we can do with mass is we can damp it. Let's talk about the mass of a 2x4 wood stud wall with gypsum board on both sides, right? The gypsum board is good mass, but it resonates. As a tuning fork would be resonating when you've got it in contact with your desk after getting it excited. When you touch that tuning fork with your finger, it stops humming. You've damped the resonance. You've diminished the amplitude of the transmitting wave. So with something like gypsum board, we can do that in a couple of ways. We can use a viscoelastic compound between two pieces of gypsum board and make constrained layer damping, or we can use a fibrous soundboard and have and create extensional damping with just one layer and have that in intimate contact. So damped non-resonant mass is the first way that we get around mass law. Andy?
And so another method of damping mass is increased damping of a secondary subfloor increases the STC and IIC ratings. In this case, you've got a fibrous cellulose board in lieu of, say, doing the lightweight poured gypsum. Here, you're just attaching that fibrous board to the subfloor with adhesive and screws. You're not adding water, and you're damping the resonance and damping the mass. Steve?
So decoupling is the second dynamic that we like to introduce as far as using little tricks to cheat mass law. A couple of slides ago, Andy was showing you poured gypsum on a floor, and poured gypsum is just solid mass. But when you use their sound mat underneath it and decouple it from the subfloor, now you're going a step further. So true decoupling would be a double stud wall. You can see there that there's the sound wave can be traveling through the wood studs at approximately 12,000 feet per second. When it comes into that air pocket, it has to slow down to 1,200 feet per second, and that shears the sound wave off into shears off the acoustic energy into heat energy. You can also decouple the wall using resilient channel. I'm sure most of you are familiar with channel. Not only does resilient channel decouple and add that airspace, but it gives us the third little way that we're getting around mass law, and that is planar flex. If you have a flexible wall plane, when the sound wave hits it and it is able to flex just a bit, it shears that energy off. One of the problems with resilient channel is that it's very easy to short out the wall. If you put as few as 6 or 8 screws through the channel and into studs accidentally, you're going to lose 2 or 3 or 4 decibels of sound transmission loss. One way to get around that, of course, is to use sound isolation clips with hat channel. The hat channel gives you the standoff from the wall so that the screws can't get through into the studs. And while we have this slide here, notice the holes in that resilient channel, the oblong shaped holes. This would be an example of common RC1. There is a better channel out on the market called RC Deluxe that has a dog bone shaped hole. This channel is patterned after the original RC1 from 1962 that was discontinued in the late 60s. Just that little extra shape in the holes, when properly installed, is good for 1 to 2 STC points. So it's a good thing to keep into your designs. Andy?
Here you go.
Yes, thank you. So the main thing that you're doing within assembly is creating a mass assembly. This is the main way that we're cheating mass law. You're creating an air pocket that the sound wave gets trapped in. It resonates back and forth. And in that pocket, the air is able to absorb the sound. We can put a little insulation in there, and that helps the air absorb the sound. It's very important to have all of the planes of material, the leaves of material, only on 2 sides of the wall. If we go to the next slide, Andy, we can address that. So multiple leaf assemblies can be problematic. Let's just look at the far left assembly where you have 4 planes of mass. That's a lot of mass in a wall, but you still only have STC 44. in a double wall assembly. And why is that? It's because you have that tiny little cavity between the planes when you put the planes of mass in the septum of the wall, and it's creating resonance. It's like when you listen to a seashell and you hear the shore in the shell, you're hearing the air resonating in the cavities inside that shell. Just by removing one of those planes of mass, now you have less mass, and yet since you have a larger cavity, the STC goes up to 53. If you do it the right way and you have what we call a two-leaf assembly with 9 inches of airspace between them, you've got the best STC 63. Also, it's good to note that if you're trying to design for low frequencies, the wider the airspace like that, the better the wall will handle those low frequencies. Andy?
So here we're talking about an enhanced gypsum wallboard. We're still damping mass by putting a high density core and a viscoelastic polymer, a thin layer between those cores, and it's constrained layer damping. So 2 layers, and it's damping the mass. And now absorption through insulation inside the wall cavity takes place inside the wall cavity or floor and ceiling cavity. And insulation in these cavities increases the absorption. Like we were talking about the NRC, insulation is almost perfectly absorptive, a 0.9 NRC. This is what's stopping the sound from going through the wall. The insulation type's not critical so much. Rock wool performs only slightly better than fiberglass, and foam insulation will not perform as well as porous insulation such as fiberglass.
So unbalancing is the next way we're going to talk about getting around mass law. So there are 2 ways to unbalance a wall. The first is to unbalance the cavity. We spoke about cavity resonance a couple of slides ago when we were talking about the multiple leaf construction. The cavity is an important part of a 2-leaf assembly, but it can also cause problems because when a 2x4 wall is built with gypsum board on both sides, as it usually is, it's going to resonate at around 125 hertz. That resonance dip in a test is going to kill the test. One way to get around that, because it's a very symmetrical resonance, one way to get around that is to replace one of the sheets of gypsum board with a fibrous soundboard, a cellulosic soundboard. That has a noise reduction coefficient that's higher than sheetrock. So sheetrock, as Andy mentioned, is 0.05 NRC, which is very reflective. A cellulosic fiberboard with a noise reduction coefficient of 0.20 is absorbing a little bit more sound. So that resonance becomes asymmetrical. It gets unbalanced, and you can lower that 125 hertz troublesome resonant zone down to 60 or 80 hertz. Not only does it get it out of the critical range of the sound test, but it actually makes the wall sound better. The second way to unbalance a wall is to mix up the planes of mass on the wall. When we do that, we're playing with critical resonant frequency. Each plane of mass, each plane of material has a resonance at which it, as a frequency which it resonates at. For instance, a 5/8 piece of gypsum wall board is going to resonate at 3600 hertz. That means that the 3600 hertz part of that sound wave gets a free ride through the wall, goes right on through. And that's a problematic zone for human hearing, harmonic area. A 3/8 inch thick piece of gypsum board is going to resonate at 4000 hertz, and a piece of fibrous soundboard, a cellulosic board, will resonate at 4400 hertz. So by mixing those planes up in the same assembly, you're unbalancing the wall, and you can take that coincidence dip that you can see circled in red, and you can make it shallower, and you can also move it further up into the higher frequencies where it's not so problematic. And then this way you're unbalancing the wall through planes of material. Andy?
Thank you. So another thing we can do is we can add membranes to the floors. Adding membranes under the finished floor protects or prevents the impact sound wave from fully developing. So you might put rubber membranes down or cork membranes down And floating floors that are so often used in an LVT example work best over a thin membrane. Adding membranes to wall, we could talk about mass-loaded vinyl, a vinyl sheet that's been impregnated with a metal compound, barium, to create a thin and malleable sheet of mass. Mass-loaded vinyl is loosely attached to framing members to create a limp mass barrier to be used with gypsum wallboard. It will not work well between the planes, and it will not provide code-compliant sound control by itself. We can talk about acoustic sealants. We talked about not having the floor and the floor and the ceiling connect to the walls, leaving a gap there. So leave a 1/4 inch around all perimeters to take away the physical transmission path and then allow for the acoustical sealant insulation. Put a backer rod in there first, and then the sealant over the top. The backer rod's going to keep it from migrating. And then seal all incursions like outlets and ceiling lights where there's openings as well. Here's a number of different components that we can add to get improvements. These are approximate improvements. So starting with a wood fiberboard, you can change the decibel by 1. Type X gypsum wallboard, 3 decibels. Type C gypsum wallboard, 4 to 5. Insulation in that wall cavity, 4 to 6. RC channel that we talked about, 6 to 8. Isolation clips, 8 to 10 decibels. Mass loaded vinyl, 9. A cellulosic fiberboard, 10 to 12. And specialty drywall, 10 to 12. So again, I guess it's a combination of looking at the cost of each one of these and the gradual increase in improving the sound. And finally, the last section is addressing the sound control issues. So unimproved assemblies, you're going to start with a wall like this. You have an STC of 36. It's a common wall. We know that that's not a good enough between living units, and we need to get to an STC of 50. So what do? Steve?
Well, we can start by adding mass. And let's look at these first 3 assemblies from the left that are really depending just on mass. Of course, it starts with your mass air mass assembly, which has got just a 2-leaf assembly and a cavity in the middle. So just with gypsum board on both sides, you're in the range of STC 34. Add some insulation into that cavity, which helps, excuse me, folks, it helps the absorption in that cavity. And you can pick that STC up to 36 to 38. Add an extra layer of mass, and now you're dealing with mass law, remember? You have to double the mass to get 6 decibels. Now you have a wall that's got 2 layers of gypsum board on each side of the wall, and you still have not achieved STC 50 code. But when you go to the next assembly, which introduces resilient channel under one of those sides of the wall, now you've reduced one of the layers of mass, but you're cheating mass law. You're using one of our little tricks by decoupling the wall and adding planar flex, 2 of our little tricks. And now you're at code. So then you start to decouple the wall with a staggered stud assembly. Remember that when you're staggering the studs and you have 2x6 plates and 2x4s staggered on them, you're still transmitting some sound through the top and the bottom plate. But now your STC has gone up well into the above code territory. And then, of course, true decoupling, true physical transmission path removal, and you have a wall that's into the higher ranges of into the 60s, which is, so now you see the difference between using straight mass and using the little tricks to cheat mass law. Let's go to that next slide. Thank you.
Yep.
So here we have cheating mass law. And let's look at some typical ways that we're doing this and how we've accomplished it. On the far left, you have a 2x4 wood stud wall with resilient channel. What's that channel doing? It's decoupling the wall. And what we also learned that it's establishing planar flex. Now that channel is probably an RC1. It's not going to make code, and that's what most folks are using. If you go to the RC Deluxe, there are some tests out there on the marketplace that show that it does make code using decoupling and planar flex. On the far right, you have a 2x4 wood stud wall. This wall is built with the studs on 24-inch centers. So right away, you're introducing more planar flex. This wall also is made with a constrained layer damping from specialty drywall, which you'll remember is 2 layers of drywall with a viscoelastic compound between them. Again, if this wall was tested with 16-inch on center studs without the planar flex, that STC would probably be around 48. In the middle, we have the best of all worlds. You've got a cellulosic fiberboard that allows you to decouple the gypsum board because it can hold the screws. With the gypsum board not screwed through to the studs, you've created planar flex. With the gypsum board in intimate contact with the cellulosic fiberboard, you have damped mass. That would be extensional damping rather than constrained layer damping. With the cellulosic fiberboard facing the gypsum board across the cavity, you have unbalancing because you're decreasing the cavity resonance of that wall. So using a cellulosic fiberboard in this way, you're really using all of the tricks in the book to cheat mass law. Andy?
So if you use let's compare a cellulose board versus a wood fiber board. 2 options. On the left, the cellulose sound board is a discontinuous mass of fibers held together by the surface tension of the fibers. It's strong enough to hold the fasteners of the sheetrock on the outside of it and be decoupled. So that cellulose fiber board installed on just one side of a wall gets the decoupling accomplished and gives you an STC of 53. On the right, we're talking about wood fiber boards. They're held in a glue matrix and therefore are less dense. And the wood fiber testing that comes from the companies that sell it show that it's tested on both sides of the wall only, not on just one side, and they accomplish an STC of 39. They don't offer the test where it's on just one side, probably because it doesn't gain anything greater than an STC of 39. And unimproved assemblies, we start with a floor ceiling assembly. I-joist, no insulation between it. You're going to get an STC of 37 and IIC of 32. Again, not something we're trying to achieve. Steve, here you go.
Sure. So remember we talked about the fact that with impact sound and with floor assemblies, we're talking about IIC, impact insulation class. The sound wave is generating in a different way than with STC. With your wall, as I mentioned before, or with a ceiling, the sound wave is generated in the room and it's a wave that's hitting the wall. But with a floor, it's happening right on the floor. So what you do on the surface of the floor is important. This assembly has all the classic stuff of resilient channel on the ceiling, gypsum board on the resilient channel. It's got a layer of poured gypsum, and we'll assume that it's got the sound mat as well. But what's happening on the floor is most important. So you can see on a bare floor, you have IIC 38. Add some porcelain or ceramic tile, and you still have IIC 38. It's just not enough mass to satisfy mass law and do any better. And it's a hard surface. As soon as you start adding a resilient surface, like a cushion-backed vinyl, now you start to get your IIC numbers up because you are degrading that impact wave as it's developing. You're not really letting it fully develop. You can do the same things with floating wood floors that have a little isolation sheet underneath it. Your IIC picks up. When you get to carpet, you're obviously starting to really degrade that sound wave. A thick carpet is going to do best. Even over OSB, you're going to get, without even gypcrete, you're still going to get into the 60s with sound wave, with IIC. Andy?
So when we talk about applied principles that apply to both walls and floors, decoupling, damping the mass, absorbing the sound through insulation, all 3 are the best. That's where you're going to get optimal performance. So if you could do all 3, where they overlap will be the goal and the highest performance. We always want to recommend acoustic consultants. It seems so often that most projects now have water intrusion consultants. They're standard. Moisture intrusion consultants are on every job. I think the use of acoustical consultants is also growing, and we always want to promote them as someone that perhaps an architect or building owner would consult. Some of the other benefits of a cellulosic fiberboard is that you can save 15% on your energy bills with that sound barrier panel being applied. And here's a little video. There's no sound here, but I'm just going to play this out. It's going to show a manufacturer using recycled materials that we all put out to the curb in the blue container. What you'll see here is about a 30-foot diameter hole in the floor of this factory, and it's about 20 feet deep. And this recycled paper and cardboard gets put into that hole with water and 2% paraffin. It spins, and through centrifugal force takes out anything that might not should be in there, like a piece of glass or a wire or a stone. It filters all that out, and then it processes this product into a cellulose fiber board. That vat there is 8 feet by 12 feet, and what's coming down on it is a screen that pushes out all the water in the thickness of 2 feet down to a half of an inch, or 5/8 of an inch, or 3/4, whatever their desired thickness is. Goes through a dryer and then comes out into this structural board. So post-consumer recycled content chart of all the products listed here, the only one that's less than 95% on the post-consumer percent by weight is the structural building board and substrate. But for the sound barrier paneling, the tack board, structural roof decking, cork board paneling, resilient flooring system, and interior paneling, they're all using a high percentage of post-consumer weight. Lead credit contributions, material resources, building product disclosure and optimization, sourcing of raw materials, building product disclosure and optimization for material ingredients, and environmentally preferable products. So the review is the sound control in the building industry we discussed, the building code criteria and guidelines, the control theory and terms, strategies of sound control, and then how do we address those sound control issues. So these are the objectives that we set out in the beginning, and we've accomplished that. With the few minutes that we have left, is there any questions?
I have a couple.
Sure.
Maybe you said it, but the cellulose fiberboard has been tested for fire rating.
Sure, let me handle that, Andy. So it has been, there are 2 fire ratings. There is ASTM E84 where you measure a component for flame spread, but the more important one, and I think the one that you're referring to, is ASTM E119, where UL measures for fire resistance.
Correct.
And this cellulosic fiberboard is used, as you'll see shortly, is approved for use in UL assemblies. We have 100 or so that it's used in. The gypsum board in these assemblies is always the first line of defense against the fire, and IBC has a rule that states that once you've proven fire resistance on an assembly, you can add a plane of material in any position on that assembly. But the maker of this cellulosic fiberboard, who you will soon be introduced to, has tested this as per ASTM E119 and found it, and they've approved. UL approves it for use. More questions?
Yeah, my other question was, we often get OSB in our corridor walls or something, or even in our demising walls, and that's a negative impact on STC generally. So what do you do then?
Well, not necessarily, but you can. That's a good layer of mass. So if you're just dealing with mass, you're adding mass to the wall, but OSB can be damped. It's stiffer
than the
right.
drywall would have been by itself.
Well, the reason OSB is usually in there is because they want to establish a shear, exactly, to prevent racking. but you can still damp the resonance of that wall by putting a cellulosic fiberboard directly in intimate contact with the OSB. It'll keep it from resonating. You won't have the planar flex, but you can probably introduce planar flex on the other side of that wall through either resilient channel or, again, a layer of cellulosic fiberboard. If you can have planar flex even on one side of the wall and then damped mass on the other side, you're still going to get a high STC wall.
How do we calculate that?
Well, you can't really add up the components accurately. You have to kind of try to start with a base data sound test.
Do you have a wall that you've tested or something that has OSB
Well,
in it?
We don't, but we know that OSB is going to add about the same to a wall as a gypsum board will. It's going to be slightly more dense and slightly heavier, but not by much. So you can take a base data test for a sheetrock wall and really apply that, because the dynamics are going to be pretty much the same. So you just have to extrapolate from base data, because you're never going to find testing on all of these walls.
I've been told it makes it worse in the typical
Well,
situation.
typically it does, but typically people don't realize that they have to damp that mass. If they just have that mass there as resonant mass, then it's going to transmit the sound wave readily. Once you damp it with a layer of, say, a cellulosic fiberboard with extensional damping, you've definitely reduced some of the transmitting wave.
Sure.
But that's not a typical application. That's a sound control application.
Right.
More questions?
Well, thank you, everyone. We'd like to go into the Homasote infomercial. And Homasote's in West Trenton, New Jersey. It's over 100 years old. It's the oldest manufacturer of building products made from recycled materials in the United States. If you ever have the opportunity to come up there, we would be glad to show you that factory, and it's quite an interesting tour. But Homasote 440 sound barrier has been installed in millions of square feet around the world in walls and floors for sound control. So as I mentioned earlier, when we were describing it without the brand name, it's 98% recycled content. We had 2% paraffin wax as a binder, and it allows us to have a very good relationship with water. We do add 0.1% of a copper metaborate, and it makes it so that termites don't want to eat it, and that mold is not favorable for growing on it. So important. But we're used in multifamily. I mean, that's the goal. IBC Section 1203 or Section 1206 since 2003 has given Homasote new life in these processes, in walls and in floor assemblies, to meet the STC and the IIC. And when you compare us directly to a liquid gypsum application, we eliminate 90% of the weight associated with liquid gypsum. You can get perhaps some value engineering in your trusses. It's dry, so you don't have to worry about, you're not adding water, you don't have to worry about curing the water. I've had builders tell me, we're never sure of that interior closet or bathroom, if it was fully cured before we continued on with the process of construction. Don't need specialized trade for the installation, and we do all the training of anybody that would be doing a project. And we maintain sound deadening over time. We're not worried about somebody setting a refrigerator down too hard the first time someone moves in and starting a crack that would migrate over time through the unit. So Homasote's 1.2 pounds per foot. As we mentioned, we don't introduce any water. We meet the STC and the IIC. So does the poured gypsum with the Acoustimat underneath it and the correct thickness of the pour. We're price competitive. I've seen, low and tight gyp numbers, tighter than the $250 a foot there, but soup to nuts with the screws and the adhesive and the Homasote will be every bit as cost efficient as the liquid poured gyp, and we estimate around $1.60 a square foot. And one of the nice things too is that we don't disrupt the schedule. Time is money, and if you have to wait for gyp to dry, depending on the humidity and the temperature, it could be days. With Homasote, once it's done going down, the guys walk out and the other guys putting trim on, coming on in. Start putting the trim down, adding the doors. We don't disrupt the schedule. So here's a UL L521, very common, especially now with the advance of the LVT As long as you're going with a 4 millimeter or thicker over the 1/2-inch Homasote onto the subfloor, we're damping the mass, and it's one of the most successful applications in the UL. And like Steve was saying, we're in that assembly that's UL rated. So we talked about the walls. Again, you can put Homasote on just one side of the wall. It's structural enough to hold the weight of the sheetrock. There is also some adhesive required, and then it's an intimate contact with the sheetrock. It's damping the mass, and we can get to that STC 53 with the U305. Here's some recent projects. 2010 Walnut Street in Philadelphia, Agapole Construction with the architect shown there. We found also that when you have infill projects, inner city in tight spaces where there's 1 or 2 or 3 buildings, it's tougher to get on the JIP guys' schedule, and they need product now. And we're winning a lot more of those smaller projects. And then we're becoming introduced to the builder because of the speed of getting the product. Taylor Woods, another one in the greater Philadelphia area. Tim Schaefer Communities, 300 apartments. There's some down in the DC area. So we did 14 buildings, 2/2 condos with Pulte over there off the last exit off the Dulles extension before Leesburg, and had great success with them. They saved, 2 miles of 2x6 double plate, which they would have normally put up there, and they saved on engineering of those trusses. City Center, Pleasantville, New Jersey, another project, 135 apartments. So we're getting more and more exposure, and it just, but it's so easy to call the guy who has a relationship with the general contractor, that guy being the JIP, because he was there before sound became important as a leveling factor. We want to, this is a little, just a 45-second video. We want to show you that we have a relationship with BIMsmith. It's an online platform for you to use that's no cost, and where you can put together a floor or wall assembly in about 2 minutes instead of 30 minutes.
For more than a century, Homasote has been the market leader in specialty floor, roof, and wall panel boards. No other fiberboard is manufactured like Homasote. The result is an innovative product of unmatched quality and engineering. It's because our dedication to these principles that we're excited to announce that we are BIM ready through the BIMsmith platform. Our 440 sound barrier is a uniquely high-performing product. With less material and less labor, you can expect better results. For more information or to access our BIM content, visit us at bimsmith.com/Homasote today. Homasote, sensible sound solutions.
It's an easy sign up if you go to bimsmith.com. It's just they ask for your email address. They don't ask for any other information. You make up your own password and then you have access to it. Some of the other things that Homasote does is that we take our 440 panel and we put a fabric on it. We call it design wall. We offer the Guilford of Maine recycled fabric in 3 different colors. There's many more colors, but we stock 3 different colors. We also offer a product called Pinnacle, where we take the 440 sound barrier in its gray state and we sand it on one side to what looks like a velvety finish. I call it industrial chic. Some people would buy that and just leave it raw, or it gives you a very smooth surface for painting. And then we also have another one where we put on cork on one side of the Homasote, gives you that exterior cork finish. Again, all of the Homasote 440 is a great tackable surface that doesn't wear out. We have a lot of literature in PDF form and downloads from the website. And if you ever need samples, we have these cute little 7-inch square samples of all the different products that we send to you. And it really gives you a feel for what the product's made of and how hard it is. You think something's made of a recycled paper, it's going to be easy to break. It is very dense. It is not easy to break. So thank you very much for your time today. We really appreciate it, and we'll get the credits and the certificates out to you as soon as Danny sends over that list.
Hey, Andy, Steve, there was one more question in the chat box from Anna. She was asking if there's any tips on sound control for glass partitions and doors for interiors.
Doors are a weak point. Glass partitions can be tough as well. Glass partitions are going to resonate. There's not going to be an air cavity, so that can be tricky. Glass in general, some glass panes can be double or triple pane. Triple pane is not always the best. It's the size of the air cavity in between the panes is important. Also with glass, I don't know if this works as well as in enclosures, but different thicknesses of glass are important.
Yeah. That's a big
Right.
help.
Also, with doors, one of the most important things, obviously, a solid core door is a good place to start, but the door sweep is important, and the door seals are very important. A lot of sound is leaking through. Where if you can shine a flashlight in a dark room and see it through a door, that's where your sound is leaking. Any other questions?
I have a question. Are you sole source or do you have any competition?
Well, that's a great question. We are the only source of cellulosic fiberboard. We, as Andy said, we started making it in 1909, first flatboard in 1916. You have to be careful that there are other fiberboards out there on the market, the wood-based fiberboards that oftentimes will get called Homasote generically. Homasote is the Kleenex of soundboards. So we do not have any competition. We are a very unique product, and nobody else makes it.
I remember, I'm old enough to remember when they put it on the exterior walls.
Yes, and it used to
Is that
be
the same
used
product? or
the
different?
same exact product. We make the board the same way that we used to make it in 1916.
That was black, like a dark.
Well, no, see, there you go. That blackboard was made by
Somebody else's?
Celotex. Yep, that's the
You're
wood-based
right,
fiberboard,
Celotex,
right?
Yeah.
So that's the thing. That's exactly what happens, and a lot of folks are going to call that Homasote with a small h, right?
Yeah,
The Kleenex effect.
right.
Are you still making a roofing board? A roof
We
deck?
do. Yeah, we do. We make two roofing boards. We make one for commercial called Firestall, which has the bottom layer that is a Class A material, and that can span 16 inches or 32 inches or 48 inches. We also make a product, and we have for years and years, called Easy Ply Roof Deck, which is a 2 1/16 inch product. It was in vogue back when A-frame and chalet style was when you want to look up and see the beams. It has a nice vinyl covering on the bottom, and it's a structural board that also is a nail base. So, and we still make both of those products, and those are made basically from the Homasote substrate, laminated together. Good questions. How about some more?
You can put tile right on top of this in a thin set, or you have to go to another board under it, or what do you?
We do like, and that's a good question. We do like an anti-fracture layer over the Homasote. Most tile guys are going to use an anti-fracture layer no matter what they're doing, even right over OSB. So something like, what's popular these days is Schluter Ditra, but a cementitious board has been used, or a peel and stick membrane such as Proflex 90, just something that decouples the tile so that you don't get cracked grout joints when you get the differential stresses of the building.
Yeah, that's what I wondered.
Just a typical situation.
Mm-hmm.
What else? This is good.
Thank you.
Well, thanks very much, folks. We appreciate everybody showing up. We definitely appreciate it. Thank you.
Yes, thank you very much, everyone.
Bye.
Thank you both very much. I'll get you
Have a
guys
great day.
the sign-in sheet before the end of today.
Very good. I'll issue right away.
Okay, thank you.
All right.
Thank you, Danny.
Bye-bye, folks.